Welcome. Sorry for the poor camera angle today. Let me see if I can get this a little better for the moment. That is the major part of the notes for today. I'm going to put this back down so you can pause it to see everything. Yeah, it's the best I can do for today. I'll try to update this another time. So when you get a chance to pause it and take all those notes and then go from there. The graph of every polynomial function of degree n, maybe that's helping, has at most n minus 1 turning points. A little better, yeah. If a polynomial function of degree n has n distinct, meaning different, real number zeros, n distinct real zeros, then its graph has exactly n minus 1 turning points. So the difference of exactly and at most has to do with the number of zeros that are different. Find the exact or maximum number of turning points for the function. So if this is your function, the number of distinct real zeros, remember zeros are the values that make each of the terms 0, because if a term equals 0, a factor I should say, not a term, a factor, if a factor equals 0, those are things that are multiplied to give you the whole thing. If a factor equals 0, then the whole thing is 0. And so x equals 0, x minus 1 equals 0, and x plus 3 equals 0. The zeros here are, oops, let me do that differently, are 0. Oh, I forgot a 0. How did I do that? Add 1, 1, subtract 3, negative 3. Those are the 3 zeros in this problem. Well, the other thing you need to know is the degree. Now, each of these factors, if you look at the highest exponent for the variable in that particular factor, you add them up, and that is the degree of this polynomial function. In this case, that's 3. If the degree and the number of different real number zeros is the same, it's exactly versus at most or maximum. Now, it's all, the number of turning points is always 1 less than the degree, at most or exactly, so 2 turning points. So in this situation, there would be 2 turning points. Now, let me just show you a quick sketch as to what a third degree function might look like. Here's one example of a third degree function. You have a local maximum here, because if you just look in that small focused area, in this focused area, you see there's a high point. That's called a local maximum. And then there's a local minimum here. Well, each of those max and mins, those local max and local mins, that's a turning point because the graph is going up. And then after this point, it starts to go down. So it turns. It's going down, and now it's starting to go up. That's a turn. So turning points. Now, there are other types of graphs that are third degree functions. And another example would be one that just does this. You never see it turn. I mean, it changes what we call inflection, changing which way it bends, but it never turns back into the other direction, up versus down. And so therefore there would be no turning points in this situation. But this one has exactly 2. All right, so let's look at another example. We're trying to determine if it's exact or maximum and how many turning points. So as we started this one, and we should start all of them, I should have done that before, we're trying to find the degree of the polynomial function first. Now notice this factor has a degree of 2, 1, and 1. So that's a degree total when you add it up of 4. The zeros of this, x equals 0, x equals -2, x equals -5. Now if you set each of these equal to 0 and solve, you'd get the -2 and -5. Technically, this is x times x. And if you have x times x, each of them is a 0. So I have 2 0 values for a 0 of the function. But when you make a list of possible answers, you don't normally list the same answer more than once. Even if you list it more than once, remember the zeros have to count only if they're different from each other. So there are only 3 different or distinct real number zeros in this situation. So therefore, this is going to have a maximum of n-1, n is the degree, so 4 minus 1, 3 turning points. Now you could abbreviate it TP if you like. No, that does not stand for toilet paper. It's turning points, so maximum of 3 turning points. Let's look at these two, and I want you to try these on your own, so pause it and see if you can do this on your own, and then we're going to go over it together. All right, now that you've had the opportunity to try it on your own, degree. The degree for this one, remember, a square means to write it twice and multiply. So this thing is listed twice, and this one once. Well, I've got 2 1s from this one, and 1 1 from that one, a total degree of 3. The zeros, x equals 6 twice, so we only list it once. X equals -8. This is definitely a maximum of n-1, 2 turning points. Down here, it's a little different. I've got a power of 2 and a power of 1, so again it's degree 3. When I go to solve this for zeros, we know this is -9. Let's do that one. X squared minus 7 equals 0. If you recall, the first step in this process would be to add 7 to both sides. And then we need to try to get x squared without the square. And so we square root both sides. But if you recall, the way to do that, whenever you square root a variable to solve, square root both sides to solve for a variable, you have to include the plus minus sign. And we can't simplify the square root of 7. So, oops. So what we want here for an answer is the positive square root of 7 and also the negative square root of 7. That's 3 answers and 3 degree. Those are real numbers. Square root of 7 and negative square root of 7, real numbers. Now if you had square root of -7, not a real number, complex number or imaginary. So that would not be a real number 0. But negative the square root of 7, yes it is. So the result here is exactly 2 turning points instead of a maximum of 2 turning points. If the degree and the number of real zeros is the same, it is exactly. All right, let's take a look at this example. In this example, it's a word problem, yes. And you are going to be using Desmos to try to graph it. You are designing an open box. Remember, that's sides, front, back, left, right, and the bottom, but no top. It'll be made from a piece of cardboard that is 16 inches by 20 inches. Now, if we were making this out of sheet metal, for example, and we were going to weld that seam, we would do a similar thing as what we're talking about here, except we'd cut completely off those sides. You want to have the greatest possible volume. You will form the box by cutting and folding the 4 square corners. Then you will fold up the sides. How long should you make the cuts? What are the dimensions of the finished box? So here's what your general piece of cardboard would look like. You're going to fold along these dotted lines. You're going to cut these squares out. Now granted, if it's a piece of cardboard, you'd probably just cut one of the sides and bend it so that you could attach it to the folded up side, whether with glue or staples or something like that. So this is 20 by 16 inches. Well, that's great. That's the full length of the rectangle and width of the rectangle. Now, if we're going to take x by x, each of these is x by x. I kind of put that funny on that one middle down here. Let me fix that. That's better. If that's the situation, when we bend it up, this distance is going up. So that's going to be a height of x. So if we're talking volume, x is the height. Now we need length and width. Well, if we're really doing length and width, the length, it's going to be 20 minus each of these x's. So that is going to be the length. The full 20 minus this x and minus that x. So that's minus 2 x's. And of course, this one is going to be 16 minus 2x. I don't know if that's easy enough to read. I'll put it over here. 20 minus 2x, 16 minus 2x. So if I want to know what the maximum volume, before I even get there, the biggest x could possibly be, and still have a side here and not have it cut off completely, it can't be any bigger or even equal to 8, because that's half of 16. If I made it 8, this square would go all the way here and this one here, and it would just completely cut off the side. That would be no good. So it has to be between 0 and 8. Now let's look at Desmos. This is what Desmos looks like when you look it up, D-E-S-M-O-S. Graphing calculator. Over here you have a little symbol for keyboard. You touch that, and y equals x times 20 minus 2x times 16 minus 2, 2x. Is that right? Yes. All right, now I've got my graph. Now, I'm going to have to go over to my desk to do this. I'll talk louder. Now, when I look at this, I have to back it out so I can see what's going on. And way up here, you'll find the highest point. The highest point up here is an x value of 2.945, awfully close to 3, and 420.11. That is the maximum for this. If we were to go back to the view, the home view, this shows us the x-intercepts here, here, at 0, 0, at 8, 0, and there's even another one at 10, 0. Those are your x-intercepts, or your zeros of the function. So this has exactly 2 turning points. But the highest point was 2.94 for x, and 420.11 for cubic inches of that open box. So technically, x equaling 2.94 inches, and v, the volume is 420.11 inches. Whoops, oops, 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 oops. Inches cubed. That's what I wanted. What's interesting is if we actually use 3, which most box companies are not going to use 2.94 because that really gives you messy things here. If you used 3, 20 minus 2 times 3, 6. So 20 minus 6 is 14. And 16 minus 6 would be 10. It's interesting that the volume, if we use 3 versus 2.94, actually comes out to 420 inches cubed, which is almost no difference from that other value. So that is the extent of it. You can find Desmos here, www.desmos.com/calculator. These are the assignment problems out of your book, and that is it for today. Have a great day.